To deal with multidimensional data, we need some fundamentally new idea, and the simplest possible idea we can use is something known as a quadtree. So this approach is actually really intuitive. Instead of every node having a less than and a greater than child, it has 4 children. One that's my top left children, one which is my top right children, one is my bottom left children, and the other is my bottom right children. Or you can use the terms northwest, northeast, southwest, and southeast instead. So I will be generally using these instead. So for example, if we insert Earth and then Mars, well, compared to Earth, Mars is to the northwest, it's to the top left. And so we'll always get this exact tree. There's no other possibilities. Unlike what we saw before, where if we pick the X coordinate or the Y coordinate, we get 2 different trees. Here, there's just one possible tree if we start with Earth and then insert Mars. Okay. Now it turns out that this approach will allow us to rapidly support subset, or I guess 2D range finding queries. So let's see a little example. Even though I think the idea is quite intuitive, I think it's important that we walk through an example and get a sense of how we build such a tree. So in this approach, what we're going to do is insert 5 points, A through E, and see what happens when we build the quad tree. So if we insert A, which has position -1, -1, we get a tree which has a root and 4 null links. So none of the children exist yet. If we now insert B, which is at position 2, 2, so that's up here somewhere, what child will that be? Okay, that'll be the northeast child right here, 2, 2. And B will have its own 4 links. Let's say we now insert 0, 1. Try and figure out what you think is going to happen next. So 0 is over and 1 is up, so it's somewhere in the middle. So it's to A's northeast, but that's already occupied. So just like a normal binary search tree, or just like a normal tree, we now need to go lower down the hierarchy. So we go up to the right, we see we're at the northeast position, and so from B, we're going down and to the left, which is the southwest. Okay, so that's the tree after we've inserted these 3 items. And I'm just drawing these little lines here as guides, letting you know that this is the region which is northeast of C, but southwest of B. That's what this is. This is the region that's southeast of C, but northeast of A. Okay. Next, D. So when we insert D, which is at position 1, 0, well, that's to the northeast of A, the southwest of B, the southeast of C, and so it ends up being northeast, southwest, southeast. And then lastly, we have -2, -2. Where do you think that will go? Okay, well, that is to the southwest of A, and so we'll end up in this position here. And then I've just shortened all the little lines, and we end up with, this is our final tree. This is the quad tree if we insert A, then B, then C, then D, then E. Okay. Now, just like a binary search tree, the insertion order will determine the topology of the quad tree. It could be spindly, it could be bushy. And so just to give you another example, let's say we're going to do the exact same data, but now just inserting in a different order. So if we start with D, we insert 1, 0. And the next one we'll do -1, -1. Well, -1, -1 is to the left and down of D, so it'll be the southwest child. Next comes 2, 2. Well, that is to the northeast of D, so again, it's the immediate child of D. Next, if we do -2, -2, well, that's to the southwest of A, or sorry, southwest of D, and also to the southwest of A. And then lastly, if we insert C, we end up with this tree. Okay. So the point here is that if you insert in a different order, you may end up with a totally different quad tree. So at this point, I hope it's clear how one can build a quad tree given a bunch of points, and that the exact tree you get depends on the insertion order.